Okay, so good morning. Am I audible?
Yes, sir.
Okay, thank you. So today is Thursday, the 25th of August, 2022, and it's our 8th meeting of Classical Mechanics 1 at CMI. So are there any questions before we continue? All right. I had a couple of comments. Of course, the third problem set is due tomorrow. There were some questions about whether it can be postponed. I'm afraid that is not possible. Please submit whatever you're able to do. And I will, if you try the problems out, you might find they are not so involved after all, based on what we've discussed. Yeah, I would like to mention, okay, I would like everybody to be present. On your answer sheets from problem set 2, certain comments have been made. Please do have a look. I mean, in case some people have been too brief, in which case you had to provide some details or additional steps. On the other hand, there are some of you who may have provided more details than is needed. So you can, based on that, you can make adjustments next time. Okay. Yeah, so let me begin. I need to share my screen. I have some problem with the internet once again. So yeah. Okay, so I in response to a question last time, I have mentioned a book which has some discussion of coordinate systems, I think. So this is one by Arkin and Weber. One moment. I have included that in the list of books. Arkin and Weber, Mathematical Methods of Physics, or something to that effect. I did mention the book by Kreisig on methods for engineers. Yeah, that may have somewhat less, but in any case, these are some places you could look. Okay, I am still facing some difficulty with my connection. Okay. Okay. Give me a moment. While we wait for me to sort out this problem, I gave an example last time of a function which is smooth but not analytic. That is, it all its derivatives at a point exist and can be evaluated. I chose the function e to the power of -1 upon x. Yeah, I should have. I mean, it's an okay example, except that x positive and x negative, there's slight difference. So a better example would have been e to the power of -1 upon x squared. So you can try that out. Okay, I am. So one moment. I have some difficulty with my internet connection here. So please ask if you have any questions.
So your screen isn't being shared, I suppose.
Yeah, my screen is not being shared because there is some problem with the internet. So I'm not able to, yeah, I'm trying to share my screen through a wired connection as opposed through the internet because there is a problem with that. I'm trying it once again. Okay. No, bad luck. Yeah, the sad thing is if I share my screen, I'm not able to use my stylus. So let's try again. Okay, let's hope this works. Yeah, I hope you're able to see my screen.
Yes, sir.
Okay, thank you. Yeah, I promise you I tried this out 10 minutes before the class as well and it worked. And then something changed. Yeah, so the function I had suggested or I would like to suggest is e to the power of -1 upon x squared. And you can check that if you define this as f of x, then f of 0, I mean, you can certainly plot this function and you might say it has a singularity at x equal to 0, but it's a kind of irremovable singularity. You can simply define the function through a limiting process at 0, as well as all its derivatives. They all vanish. So the nth derivative at 0 is 0. So if you were to construct the Taylor series for this function, all the coefficients should be 0. So the Taylor series as a function of x would be the sum of 0 by n factorial times x to the power of n running from 0 to infinity. So, but that is the 0 function. Yeah. So the Taylor series does not converge to the function. I mean, it converges, but it converges to a different function. So this was the problem. Okay, but this is a technical issue, mainly because somebody asked how this could happen. Let us come back to more typical functions. For instance, 1 upon 1 minus x, I invite you to compute its derivatives, say around x equal to 0, and thereby construct the Taylor polynomial and extend that to an infinite series. You will find that you get 1 plus x squared plus dot dot dot. Yeah, so the geometric series. So yeah, I think you are familiar with this example. So let me not. Another very important example is, of course, the exponential function. Where you can again do this an expansion around x equal to 0, and you get this series, which will be familiar to you. This series has an infinite radius of convergence, whereas the one I wrote for the 1 by 1 minus x function has a radius of convergence of 1 around x equal to 0. Okay, so there's these concepts. You will encounter them in your calculus or analysis classes, more precisely defined. Okay, an extremely useful series is the so-called binomial series. 1 plus x to the power of nu, where nu is some number, maybe real, complex, integer, non-integer, doesn't matter. Yeah. And this is, you can compute all the derivatives and assemble them in a series. This is that series, 1 plus nu x plus nu times nu minus 1 divided by 1 times 2x squared, and so on. So this is an extremely useful series because such a function appears very, very frequently in many scientific problems. And it converges for mod x less than 1. Yeah, so we often use this Taylor polynomial as an approximation. Okay, so let me stop with one variable series with that. Any question about what I've said here? Okay. I want to briefly mention that this concept extends, the concept of Taylor series extends also to functions of two variables or several variables, which we very, very frequently encounter in physics. So suppose I have a function of two variables, f of x comma y, real valued for definiteness here. So then the first approximation, you want to develop a Taylor development around a point, say x naught, y naught. So the first approximation would simply be the value of the function over there. And then you have two linear correction terms, proportional to x minus x naught on the one hand and y minus y naught on the other hand. And their coefficients are the derivatives, more precisely the partial derivatives of the function in the x and y variables, yeah, evaluated at the point x naught comma y naught. So in place of having just the one derivative term, first derivative term, now you have two. These partial derivatives, let me tell you how they are computed. Suppose you have some function like f of x comma y equal to x times sine of y. Yeah, let's take this function. When I say the partial derivative of f with respect to x, I mean differentiate this function treating y as a constant. In that case, so this is the derivative of f treating y as fixed. Yeah, and if I were to do that, I will simply get sine of y. Yeah, that is the partial derivative with respect to x is the sine of y, and the partial derivative of f with respect to y would be, well, will you please suggest the answer?
X cos y.
Indeed, x cosine y. Yeah.
Where does the formula come from?
The formula for what?
41.
Formula for the partial derivative, is that what you're asking?
No, it's actually okay. It's representing the functions at values x comma y in terms of its partial derivatives at x0 y0. So okay.
Yeah. Oh, I'm sorry. You're asking where equation 41 comes from. That is your question? Yeah. I'm sorry. You were ahead of me. Yeah. So one way to think about where this function formula comes from is I've written it here, so I will go through this. Yeah. One way to obtain this series is to treat y as fixed. Okay. So treat y as fixed. Regard f of x comma y as simply a function of x alone, treating y as a parameter. Then it is a function of only one variable. Write out the Taylor series in x around x naught. The coefficients will depend on x naught and also on y. So you will get such a series. Then we expand each of the coefficients in a Taylor series in y, because the coefficients now depend on y. If you do this double expansion, you will get some series that is this series. Okay, so I mean, that is one way to think about it. There are several other ways to think about it also. But if you accept one variable Taylor series, this is one way to get two variable Taylor series. Was that Anhad asking, or who was asking?
Yes.
Yeah. Okay. I hope that is at least partially satisfactory to you. At least is my statement clear?
Okay. Yeah.
All right. Yeah, you don't sound very convinced, but
So how would you say if you had n variables?
In n variables. Oh, excellent question. You wait. Before we go to n variables, let us finish 2 variables. Yeah. So I only told you the linear terms. Yeah, I have to go to the terms that are quadratic in the departure from x0 and y0. All right. So then there are, in fact, 4 terms to be accounted for, involving second derivatives of f. So let us enumerate them. There are terms. There is the term involving the second partial derivative of f in x. Right. So that is the first one, if you wish, times x minus x0 squared. Then there is the second partial derivative in y times y minus y0 squared. So these are the terms you might naively expect, but there is also a cross term, so to speak, that is called a mixed partial derivative, d2f dx dy. Okay, second partial with respect to x followed by y, or y followed by x. Yeah, so there are 2 such terms. I will have written them here. We include both of them, and they are multiplied by the product of the departures from x0 and y0, x minus x0 times y minus y0. Here it is y minus y0 times x minus x0. Okay. So we have these 4 second derivative terms, and okay, so this is the quadratic or second order Taylor approximation to the function around the point x0 comma y0. So let me compute d2f dx squared for the function I had written down previously, right? Can you propose the answer? What is the second derivative of f with respect to x for the function proposed here, x sine y?
0.
Indeed 0, because the first derivative is sine y, it's independent of x, so that is 0. The second derivative with respect to y, yeah, for that we take the first derivative in y and differentiate in y once again, and in that case I am going to get
Minus x sine.
very good. Yeah, minus x sine y. So we are halfway there. Now let's go to the next one, which is the second partial with respect to x following y. Okay, so that is we first differentiate in y and then in x. Okay, so let us do that. So if we first differentiate in y, we get x cosine y, and then differentiate in x, right? So what's the answer in this case?
Cos y.
Indeed, cosine y. Now let's do the other order. Yeah, this is the second, another mixed partial derivative, which is d2f dy dx. Okay, so this is a different object. I have to go back, look at the first derivative in x. Yeah, so that is over here, partial f partial x, and then differentiate in y, and then differentiate in y. So what is the answer there?
Cosine y.
Cosine y, right? Yeah, I've got sine y, and then I differentiate in y, so I get cosine y. Lo and behold, the mixed partials in this case are equal, you will notice. Yeah. Now, this is generally the case if the functions are of reasonable sort, and this is the content of Clairaut or Schwarz's theorem. Yeah, it says that the mixed second partials, namely d2f dx dy and d2f dy dx, are equal, provided the second partial derivatives are continuous. Okay, so there is a mild hypothesis, and if that is satisfied, one can show that these mixed partials are equal, so that these 2 terms can be combined. Okay, so and for your, okay, so any question about I mean about just the formula itself? That is the first stage.
So what are the other terms? I mean, half of this thing plus.
Oh, plus. You are very eager to see the rest of them. So can you tell them, okay, in the first one variable case, what was the next term? So you begin saying it.
Of course, outside the constant would be 1/6, isn't it?
You didn't finish your statement, please. 1/6. Indeed,
I mean,
1/6, or I prefer to write it 1/3 factorial.
3 factorial.
Yeah. Okay. So then I'm going to have several terms here. Yeah. So I mean, there are short ways to write it, but okay, let me write them out explicitly. There's going to be the third partial of f with respect to x, and that's going to be multiplied by x minus x0 cubed.
Cube.
Yeah. Now, this is the only term you would have if the function was a function of x alone, right? In that case, there's only one such term. But here
Yeah.
you are going to have more, and you are going to tell me all
Yeah,
these.
we'll have del 3f del y3, and after that,
Okay, y cubed, yeah, y minus y naught cubed.
then what will be the other terms?
Yes, yes. Oncon is very eager to get the rest of them. So, okay, you tell me. No, basically, you have to do all possibilities. So you would have d2f. Sorry, all are third derivatives, but you could differentiate twice in x after differentiating once in y.
Oh,
Okay, and that would what would that multiply? Please tell me.
x minus x naught square y minus y naught.
Indeed, yeah, you get the hang of it. Yeah, and then I've got more. So then, okay, let me not
Del
write all the
3.
terms, but you give me one more at least, so that I know you are on the right track.
This formula means true for all functions f, or like you have to assume them to be smooth.
No, you don't need to be smooth. This formula holds provided the third derivatives exist. Yeah. So, I mean, we are just developing a Taylor polynomial. It's a separate
No,
question.
so only these 4 terms or other terms are also there.
Oh, no, there are many more. Yeah, you need to consider all ways of distributing 3 derivatives among x and y. So 2x derivative, 1y derivative, and in all orders, right? So let's not.
Yeah, we have covered del 3f, and in the bottom we have del 2x del y, and another one del 2y del x.
Indeed, yeah, right. So you're going to get that.
Oh,
as well.
you saying that then you will have to swap, like there
Yeah.
you wrote del 2x
The
del
order,
y, then it will be,
order does matter.
yeah,
Order does matter.
okay.
Yeah. So you will have partial y, partial x, partial y. Yeah, you will have such terms in all possible orders. You have to account for. So I leave it to you to
Understood.
Yeah, okay. So yeah, anyway, you try writing this out. Yeah, so this is y minus y naught times x minus x naught times again y minus y naught. Of course, several of these terms are equal. All right, yeah, so the one where there are 2 y derivatives carried out first followed by next derivative will be the same as this term, again by a version of Clairaut's theorem. So I will leave you to imagine what the remaining terms are. Yeah, and there is an extension to 3 or more variables. Yeah, I hesitate to write it here because I think you are imaginative enough to figure this out, and there are better notations for it. So let's do it when we need it. Yeah, I know somebody asked me what about several variable generalization. I want to avoid writing it down over here. Yeah, I think this example already conveys most of it. Yeah. Okay. So as I already pointed out, the mixed second partials are equal by Clairaut's theorem. Okay. Any question about this thing about partial derivatives and okay. If not, let me proceed to my last topic in this preview, or rather a primer on some kinematics and mathematical preliminaries. Okay, so this is vector calculus, a very brief discussion thereof, which is actually an extension of what we've just spoken about. Okay, so we've talked about vectors, but now we want to take one step further and go from vectors to vector fields. Okay, so this is a big jump in some ways. So let us, but before that, I need to talk about scalar fields. All right. So what do you physically, what do we understand by these things? So suppose we look at a given instant of time, then, and I consider the pressure in the atmosphere. Yeah, suppose the atmosphere above Chennai. Yeah, so the pressure is a real number that depends, of course, on height and more generally on the location. Yeah, so the location where above CMI. Yeah, so the pressure is a function of location. It varies from place to place. Similarly, the density of seawater at a given instant of time depends on the depth. into the sea, and of course, where you are located, how far off the coast, and so on. Yeah, so that is again a real number at each location. Okay, so that is a second example of what we would call a scalar field. So by scalar, we simply mean a real number. Now, a scalar field is a real number that varies with location. Okay, so that is a simple way to think about it. So similarly, you may have the salt concentration of seawater, C of R. That again depends on the location. Yeah, I mean, near the mouth of a river, the salt concentration may be higher because the water is bringing salt from the earth, from the land, from rocks, and so on. Similarly, the potential energy, yeah, we've not talked about energy very much, but I can let you imagine the potential energy of a massive particle in Earth's gravity depends on the height above the Earth's surface. Yeah, I mean, if you're higher up, the potential energy is somewhat more. Yeah, so that potential energy is again a function of location. That is another example of a scalar field. So a scalar field is simply an assignment of a real number to every point in a certain domain. Yeah, so all these are examples of real valued functions in three-dimensional space. We will refer to such real valued functions as scalar fields. Okay, so that is the technical jargon. So a scalar field assigns a real number to each location R. Of course, to be of something we can deal with, especially given the word calculus, you would like that real number to vary smoothly or at least continuously differentiably as the location changes. Yeah, so as the location changes, the pressure, at least in some approximation, would vary in a continuous or even differentiable manner. Yeah, at least you would like to model it that way. Okay, any question about our definition of a scalar field?
Does scalar field have any relation to the algebraic field? Or is
Okay, indeed, it's a good question, and that is the next paragraph. Note that the notion of a field introduced here is different from the algebraic notion of a field, such as the field of real or complex numbers, yeah, or other types of numbers. Yeah. Here, field refers to something that depends on location. So that is the sense in which the word field is used here. Unfortunately, the same word field is used for both the algebraic concept and the sort of geometric and analysis concept. So you will have to decide from context what we are talking about. So is Ryan's question answered?
Yes, sir. I just had another question. A scalar field is something which you multiply to a vector, right? For example, so
You
how
can.
would you
No,
Yeah.
see, you are not obliged to go. Scalars are real numbers. If you want, you can go and multiply a vector by a scalar and get another scalar, get another vector. Yeah, so you are free to do that. I think that's what you are talking about. But those real numbers have an existence of their own. They are not only in the business of multiplying vectors.
Understood, sir. Thank you.
Okay, yeah. But they do play that role very prominently. So as on cue, let us move to vector fields. I mean, if you don't like the name scalar field, simply think of it as a function. Yeah, a real valued function of 3 variables. That's it. Okay. Any other questions? Okay. Let's see. I had additional comment. Yeah. So it has come to my attention that let me mention that yeah. So the problem sets and exams and other such things are to be done by each of you individually and written up, understanding what you have done. Yeah. So that is the stated idea. And any sharing of answer sheets or asking others for their answers and using them in yours, copying them are all forms of cheating. Whether you provide your answer sheet to somebody else or another person takes it from you, are all constitute cheating. So this has been a problem, and if you are involved in any of this thing, please come and speak to me. We will consider if you have some explanation. But I will make it clear that such practices are not tolerated at CMI and or anywhere else, and will invite severe penalties. Okay, so let us now. So I would like you to take this seriously, and if you have. If you are unsure about what you have done, please speak to me and clear your mind. Yeah, if things go, it will not be pleasant if you are involved in these things. Yeah. Okay, so let me go further now, leaving behind scalar fields to what are called vector fields. Yeah, so we've already talked about vectors. I mean, a vector is simply an arrow, yeah, at a point. But suppose we extend that somewhat. So we will now talk about the concept of a vector field. And by that we mean a smoothly varying vector v of r at each location r. Okay, so at each location r, we have a vector. So at each location in this room, one can imagine having a vector. That vector may be the instantaneous direction in which the air is moving. Yeah, so near the window, the air may be flowing this way. In some corner, it may hardly be flowing. Yeah, near an air conditioner vent, maybe flowing in a particular direction. Yeah, so the direction of the velocity of air in a room constitutes a vector field. It's a field because the vectors depend on location. Yeah. Another nice example is the gravitational force felt by a point mass m at various locations and heights above the Earth's surface. Okay, so at different heights above the Earth's surface at different locations, you can consider the force. Yeah, the gravitational force felt by a point mass. Generally speaking, this force points downwards. Yeah, the magnitude, of course, depends on location. The higher up you go, the force could be more. Yeah. Yeah,
And also the direction also depends.
Indeed, the direction. I mean, if you have yes. I mean, if you go very far away, the sun will play an important role, and the direction may be more towards the sun than to the earth. Yeah, indeed. Or if you have a very big hill, yeah, that hill will affect your gravitational force. I mean, to a small extent. Definitely, it depends on direction, and since the earth is roughly spherical, different points, it varies. Yeah, what is down is a concept defined with respect to roughly the center of the earth. Okay, so is that clear as to what? So let me give you some simple examples of vector fields displayed on the plane. So these are vector fields on the plane. So we've got 3 vector fields on the plane. We can think of at every point the vector having 2 components because we are on the plane, say in Cartesian coordinates. So a vector field on the plane may be regarded as a map from the plane to the plane again. Yeah. So because at every point x comma y, you have a vector v of x comma y, which itself has 2 components, which can be written as vx x hat plus vy y hat. Yeah, so you have to specify 2 numbers at every location. You have to specify 2 numbers at every location, namely the 2 Cartesian components. Yeah, and that is why you can think of it as a map from R2 back to R2. Okay, so I mean, if you really wanted to, I would rather think of it as a smoothly varying distribution of arrows at every point. Okay, so the first vector field, I think the picture will tell you, doesn't have any component in the y direction. So we can conclude that the first vector field is basically proportional to x hat. Yeah. Yeah, that is, I hope, plausible. The second vector field, you will agree, points radially outwards. Yeah, from that center, from this point, points radially outwards with a magnitude that increases with the radial distance. The arrows are supposed to, the length of the arrows are supposed to give you the magnitudes. Furthermore, it is a circularly symmetric. The picture is meant to convey that the lengths of the arrows do not vary as you go around a circle of a fixed radius about the center. So we will call this a circularly symmetric vector field on the plane, which is radially directed. And since its length increases with radius, it's reasonably plausible that the second vector field is perhaps proportional to the radial the radius vector itself. Yeah. So V of R may be proportional to R itself. Are you comfortable with what I have said? Any questions about this? Okay, so we're just looking at the picture and trying to figure out what kind of vector field it is. Okay, that's all. The third example, I'm not going to propose a specific formula for it. It has both horizontal and vertical components, this vector field, and you might imagine that is the vector
do you mean the absolute value of R? V of R is proportional to the absolute.
Oh, no. I mean, see, V of R is itself a vector at every location R, right? So,
So you mean that the absolute value of V is proportional to the absolute value of R?
That would in particular be true. Yeah, but more is true. I am actually saying, let me be specific. Let me say, suppose it's actually equal to R. Yeah, forget about that proportionality constant. Maybe it is 1. I will choose units where it is 1. And so I am proposing the vector field V is equal to R. Okay, I am considering this vector field. Let me plot this for you. At the point 0, 0, what is this vector?
Zero vector.
Zero vector. So no arrow to be drawn. Yeah. So suppose I go here. So I can of course write this vector in Cartesian coordinates, which we like a lot. So R is going to be x times x hat plus y times y hat. Okay, that is another way to write it. Yeah, I didn't mean to put any dot there. Yeah. So if I go to this point, at that point, please tell me how this vector points. The vector field points.
Okay, I got it. Okay.
Okay.
By that, okay, you mean that V of R is equal to alpha of R, like alpha times R, where alpha is a constant.
Yeah. No, I lost you.
R vector.
Yeah.
So by saying that vector is proportional to another vector, you basically mean it's equal to some constant multiplied by
Yes,
okay.
I could have considered the vector field 2R. Then I will have a 2 multiplying all of this. Yeah. So this is a legitimate vector field, but it's important that both left and right sides contain vectors. I mean, otherwise the formula doesn't make sense. Okay, so over here, of course, it is x is say 1 and y is 0, so the vector field points rightwards. If I go here, there are both x and y are 1, so the vector field is going to point towards the northeast. And then you can continue and draw your little arrows. The arrows are going to become longer as you go out, because at x equal to 2, the length of that arrow is going to be somewhat more. Okay, any question about how we talked about this example? Yeah, so the third example here could plausibly be the velocity vector field of a steadily flowing fluid, okay, through some, say, a curved pipe. Yeah, this may be the kind of velocity field that one observes.
Sir, will we be given any kind of question where we will have to identify the nature of a vector field from a diagram?
That question has already been posed to you. So yes, you can certainly, yes, that is a fair type of inference you could be asked to draw. Sure. Yeah. Yeah, but I mean, we're not going to draw some very complicated figure and ask you to write a formula for it. Yeah. So we have a certain collection of examples that we are developing. So as long as you have some comfort with those, you should be fine. And there are going to be more such examples. Okay, so now let me talk about the next concept, which is, see, we've simply defined a vector field and we've defined a scalar field. And as one of you pointed out earlier, you can take a scalar field f of r and multiply it by a vector field and get another vector field. Yeah, see, previously we only multiplied by 2. You're not obliged to multiply by simply just numbers. You can multiply by a number that depends on location. So I can rescale a vector field by a position dependent quantity. I will still get another vector field. The arrows everywhere will give me some insight. How do the directions of the arrows of this vector field f times v, how do they relate to those of v? What changes at what
The
does
direction would remain the same, but it will either be elongated or shrunk.
Indeed, very good, very good. So who said that?
So this is Mayur.
Mayur.
Sir,
Shastri.
direction may not remain the same, right? The field value can
It
be
may
zero.
get opposite.
Okay, it may become opposite. Thank you. Yes, yes, indeed. Yeah. Sometimes we are a bit careless with that. Even if when we say one direction, even the reverse of that direction is part of that direction. We sometimes are a bit careless about that. It's okay. Yeah, but if we can be precise, it's okay. So, but you got it right, Mayur, as well as Ryan. So, if you multiply a vector field by a scalar field, then generally the directions of vectors do not vary unless, of course, f happens to be negative there. However, the lengths of vectors at points get modified, generally speaking. So are others also comfortable with this? So, I mean, if I start with the vector field r and multiply it by 2, then I will basically elongate every vector to twice its original length. That's all that's going to happen. Okay, now we want to do calculus. We have defined a vector field and a scalar field. Now let us see how we can do calculus with them. The first object of interest is the gradient. So the gradient is the generalization, if you wish, of the first derivative. Yeah, or when you're talking about functions of several variables, it would be the set of first partial derivatives. Yeah. So let me tell you what that is. So let's suppose we are given a function, a scalar field, phi of r. Yeah, r is of course x, y, z. Yeah, in Cartesian coordinates. Now its gradient is a kind of first derivative that produces a vector field, which is denoted nabla phi of r. So this inverted delta symbol is called nabla, but we usually call it grad here. Yeah, so we call this grad phi. Nabla is the Greek letter, grad is the mathematical name because you're taking a gradient. Okay, so nabla phi, or the gradient of phi, by definition is a vector. It's a vector field, in fact, whose components in the x, y, and z direction are given by the first partial derivatives of phi with respect to x, y, and z respectively. Okay, so we have defined our first quantity. I mean, interesting.
Can you please explain gradient once again?
Yeah. I've not gone very much into gradient, so I've just given a definition right now. So suppose you have a function. Let us do an example. I think that will help Ankon. Suppose we have a function phi of xy is simply x. Instead of 3 dimensions, let's work in 2 dimensions. Phi of xy is simply x. Let us compute its gradient. Okay, so the first job is to compute its partial derivatives. So partial phi partial x is 1, and partial phi partial y is 0. I hope you will agree with me on that. Okay, so then I assemble these into a vector called grad phi, which will be partial phi partial x times x hat plus partial phi partial y hat. And I just insert the coefficient here, 1 times x hat and 0 times y hat. Okay, so this is simply x hat. Okay, so
So visually, is this like that? I mean, you are plotting a 3D surface, and in the x-hat direction, you are taking the derivative, and in the y-hat direction, you are taking the derivative like that.
that's true. Yeah, we are taking the derivatives in the cardinal directions. Yeah, the east and north directions, for instance, and keeping those derivatives. I mean, those derivatives are really partial derivatives, and we assemble those partial derivatives as the components of a vector. That's what we are doing. I will pictorially explain this as well. There's a lot of nice geometry over here. Yeah. Yes, please.
Sir, is the gradient geometric like identity? Can we change the coordinate system, take a gradient and change the coordinate system back? Like, will that remain same? Like gradient in geometric property of that vector field?
Correct. Yeah, the gradient is not simply any old collection of 3 numbers which depend on location. The gradient has a geometric significance as a vector field. So if you were to express it in one coordinate system and then switch to another coordinate system, the length of the vector at any physical location will not change, nor would its direction. Okay, so you said something. I would like to say something in a related manner. The choice of coordinate system to express a vector field does not affect the length of the corresponding vector at any location. Yeah, that is God given. You choose your coordinate system as you wish, but the length of the vector is all the same. So is its direction. If it pointed towards my nose over here, it will point towards my nose, no matter whether you use Cartesian or polar coordinates. So,
so what if it is not an orthonormal coordinate system?
No, there is no necessity that it be an orthonormal coordinate system. Absolutely, you can use any coordinate system you wish. That will not, the formulae will be a little bit more complicated perhaps, but there are circumstances where we need to do that. So no, the direction of a vector is a geometric or physical concept. It has nothing to do with what coordinate system you use. It is defined relative to measuring scales. The length of a vector is defined using a measuring scale. The direction of a vector is defined using celestial objects like Jupiter and the sun and such things. So they don't depend on whether your coordinate frame is orthogonal or not.
Thank you, sir.
Yeah. And as you said, you could do some switching, repeatedly go from Cartesian to polar and back to Cartesian, you will come back to the same vector field. Okay, so let us continue answering Oncon's question. Let's give you one more example. Oh, okay, maybe I should give you, by the way, we have met this vector field before, right? In the previous page, it is this vector field. Yeah, this vector field. Namely, this is the x hat vector field, or no, what did I do? Yeah, it's the x hat vector field. Yeah, so the length of the arrows don't change with location. Notice that, right? So the lengths of the arrows are all the same everywhere. Yeah, and that's why we say it's a vector field x hat. Yeah, of unit length everywhere. So we've just realized that the vector field picture that I drew there can actually be realized at the gradient of some scalar field. And which scalar field is that? It is simply the function phi of x equal to x. Are you okay with this little observation? Okay. So we are saying that the gradient of phi points, it's a constant vector field. When I say it's a constant vector field, I mean that all its components in the Cartesian coordinate system are constant. Yeah. Or and furthermore, it points in the x direction at all points of the plane. Points in the x direction at all points of the plane. Okay, let's take an example in 3 dimensions. Let's take the function phi is equal to half x squared plus y squared plus z squared. Okay, so this is a nice little quadratic function, and let's compute its gradient. So I must compute all the first partial derivatives. So the first partial in x is going to be given only by the first term contributes, I'm going to get half times 2x, and that is simply x. And similarly, the partials in y and z are given by y and z respectively. So I assemble those three partial derivatives into a vector multiplying x hat, y hat, and z hat. Take those linear combination. So this is the gradient of phi. Any question about how we computed the gradient of this phi? So at any location x, y, z, grad phi here is a vector that points radially outward, because we recognize this vector as simply r times r hat, also known as simply the position vector of that point r. So the vector field we talked about earlier, of course, that was on the plane, but you can extend it to three-dimensional space, is actually a gradient vector field. It's a gradient of this nice little function. Would you say that this is a constant vector field? I mean, the one that I've just worked out, grad phi, would you call it a constant vector field in any sense?
No, sir.
No. Well, for instance, its magnitude doesn't even stay fixed from with location. Here, I mean, the magnitude is increasing as you go further and further from the origin. Okay, so this is certainly not a constant vector field, and its direction also keeps changing. Yeah, it points radially outward. So it points radially outward. I'm drawing a two-dimensional slice, and as you go outside, the lengths of the vectors become even longer. So this is a vector field which we can get from taking a gradient. Okay, so now I have some further geometric insight to offer. This requires a little bit of understanding. I mean, I'm going to combine several of the things we have done today. So please pay attention. And if you don't follow the first time, please take a second look at it in your at your leisure. Okay, so I'm going to give a geometric interpretation for the gradient. Okay, so I hope this will continue answering on question. I claim that at any location r, at any position r, the gradient of a function phi is a vector that points in the direction of most rapid increase of phi. Okay. So phi is a function defined in this room. I can go to my interesting point like the tip of my nose and ask in which direction this function changes most rapidly. Not just changes, increases most rapidly. And grad phi points in that direction. Okay, so is the statement clear? Let us verify this statement in the two examples we've looked at here. In the second example, yeah, this was our function phi. We notice that this function phi, this function phi is constant on what? Please advise me.
A sphere.
Exactly. So this function phi is constant on a sphere centered at the origin, right? On a sphere centered at the origin, this phi will take a common value. If you go to a concentric sphere that is lying outside the sphere, phi will increase. If you go to a concentric sphere lying inside the one considered previously, phi will decrease. Okay. I hope you are comfortable with that, because phi is simply 1/2 the square of the distance from the origin. That is the meaning of phi, 1/2 the square of the distance from the origin. And that, of course, monotonically increases as you go away from the origin. Now, if my geometric interpretation is to be trusted, it tells me that the gradient must point in the direction of most rapid increase in phi. So you have these concentric spheres and phi increases as you go outward. So grad phi should point radially outward. Yeah, I hope that is what you must expect. Are you able to follow that? For instance, we cannot expect grad phi to point tangentially to a sphere. Suppose I have one such sphere, phi is constant on the sphere. If somebody tells me that grad phi points tangentially to that sphere, that can certainly not be the case, because if you make a small step along the sphere, phi simply won't change. So no matter what you do on the sphere, phi is not going to increase. So grad phi certainly cannot be tangent to the sphere. In fact, it must not have any component tangent to the sphere, because if it has a component tangent to sphere, you can straighten it out and make phi increase more rapidly. Yeah, I hope you get the intuition. Along the sphere, phi doesn't change. Orthogonal to the sphere, phi changes very fast. I mean, the fastest it can. There are, of course, two options. You either go outward or you go inward. If you go inward, phi will decrease very rapidly, most rapidly. If you go outward, it will increase most rapidly. Is this intuition understandable?
Sir, can we prove that the nabla phi dot some direction vector will be the difference, the differential of the scalar field in that direction?
That's right. Yeah, it's called the directional derivative. So we have a direction vector v, and you take v dotted with nabla phi. So this would be called the directional derivative of phi along v. Okay, so your idea is correct. This will tell you how phi changes when you proceed infinitesimally along v at the location considered. All right, so that we are in fact going to use that interpretation, that property. Okay, so in the next couple of minutes, I want to argue why this is the case. Okay, so but any question before I go there? Okay, so I mean, I really would like to be told if I'm going too fast or too slow for that matter, and I know that this depends on each student, has a different pace. So please don't hesitate to tell me if I am proceeding too fast or you want some clarification. Okay, so to see why it is helpful to introduce the level surfaces of phi. Okay, so we already found that useful for this nice little function x squared plus y squared plus z squared. The level surfaces are the surfaces on which the function is constant. In this case, they were concentric spheres. So, but we can apply this idea to any function, not just the square or the distance from the origin. So we introduce the concept of level surfaces. These are surfaces in three-dimensional space on which phi is a constant. Okay, so in this case, they were concentric spheres. Okay, and as we discussed in this example, for phi to change most rapidly, we must move r. Okay, we start at some location r. We must move from r along a vector that has no component along the level surface through r. Okay, so let's see if we understand what's meant. So you have a point, you have of course defined a function phi, and what we said is that if you move tangent to the level surface, your function is not going to change at all. If you move slightly off, well, the function will increase, but not that much. Somebody will tell you, why go that way obliquely? Why not go orthogonally? Then your function will change more rapidly. Okay, so that's the idea.
Sir,
So,
how can we say that there exists a level surface, or do we assume that?
No, we are assuming that the function is suitable, reasonable, such that there are level surfaces. Yeah, yeah. So with some mild hypothesis, functions will, because after all, you're taking one, imposing one condition on three variables. All right, you have three variables x, y, z. Phi of x, y, z equal to constant, like constant 1 is one condition on three variables. There will be a two-parameter family of solutions, generally speaking. That two-parameter family of solutions defines a surface. I mean, I said it in a fancy way. Are you able to follow, Ryan?
Yes, sir. Like we take x plus y plus z equal to 1, we are imposing one condition, one constant condition on three variables. It
Yeah.
forms a plane, which is two-dimensional.
Correct, exactly. Yeah. So that is the intuition that works whether your function was a linear function that you took like x plus y plus z, or a quadratic function like I chose, or any more general function. That general statement is true. If you impose one condition among n variables, you will get an n minus 1 dimensional surface. At most points. I mean, there are exceptional points where this breaks down. Even in this example, it breaks down. Suppose you go to the origin, yeah, and you look at what is the level surface of phi with value 0. That is just a point. Phi is 0 only at the origin. That is not a surface. You might say it's only a point. Yeah, but there are always usually such exceptional points or exceptional places where the level surface turns out to have lower dimension. Yeah, that can happen. Is that understood? Okay, so let me proceed with this argument. Yeah, I want to. Yeah, so the idea was that we must proceed not along the level surface, but orthogonal to the level surface if we have a chance of making phi increase most rapidly. Now, what we're going to do is we will argue that at any point r, grad phi of r is in fact orthogonal to the level surface through r. Okay. So we're going to now argue that the gradient points orthogonally to the level surface. Let us see how this is done. Now, suppose V is a vector at the point r of a small magnitude. Okay, so we go to the point r and imagine proceeding in a direction specified by the vector V. Okay, and we're imagining making infinitesimal changes. Okay, small changes. Okay. Then let us use the linear Taylor approximation for the function at that location. Okay, to compute what phi at the new location is compared to phi at the old location. Okay, so we have gone from r to r plus v, okay, nearby point. We want to compare the values of the function at the 2 points. Okay, that is what Taylor helps us do. It tells us that phi at the new location, namely phi of r plus v, is equal to phi of r to first approximation. It's the value at the original location plus a term coming from the first partial derivatives. Okay, so let me explain that. Just take one moment. Yeah, so now you will see that partial derivative formula written in a better way. Yeah, I remember I wrote it down in gory detail. All these, there are two first partial derivative terms here. They can be written in vector notation in a much nicer way. Yeah, so let me combine these two terms. You will hopefully agree with me that this is the gradient of f dotted with r minus r naught. Let's see if you follow. When I say gradient of f, what do I mean? I mean partial f partial x, comma partial f partial y. I'm writing the I'm writing it in 2 dimensions because that was this example. Yeah, so I'm writing the Cartesian components, and then I have the Cartesian components of r minus r naught. They would be x minus x naught, comma y minus y naught. Okay, so you notice that when I take the dot product of these two vectors, namely the gradient vector and the displacement vector, I will get two terms, namely partial f partial x times x minus x naught, which was the first term here. And the second term is partial f partial y times y minus y naught. So that's the second term. So you notice that the linear terms in the Taylor series can be expressed in terms of the gradient of the function in a very nice and compact way. Any question about how we wrote this? Okay, so I'm now going to use that notation and not write out. Yes,
Sir,
please.
could you please just go one bit to the left of the page? I cannot see the expression.
Yeah, I'm sorry. My paper has become very.
Thank you, sir. Yeah, thank you.
Okay. All right. Fine. Okay. Yeah. So the message is, if I have a function phi of x, y, z, or any number of variables, phi of r, generally speaking, and suppose I shift it by a small vector v, yeah, then the Taylor series is going to be phi of r to begin with, plus v dotted with the gradient of phi at the original location, plus terms of order v squared. Okay, so that's how the thing develops. When I say terms of order v squared, it involves the second powers of the components of v. That's what I mean. Okay, so I'm not writing those in detail, but this is the essential simplification in the Taylor series if I use vector notation. Any question about this? Okay. If not, let us now use this formula where we need to, going back to where we stopped. Remember, we took a small step from r in the direction of v and asked, how does the function change? Now we have an answer to that question. The change in the function, namely phi of r plus v minus phi of r, is equal to v dot the gradient of the function. Okay, that is what we have concluded, that this is true if you are nearby enough. Okay, there are of course quadratic corrections, but if you are sufficiently close by, they can be ignored. Now let us interpret this formula. Suppose v is tangent to the level surface through r. Okay, suppose v is tangent to the level surface through the point. Yeah, v is tangent. Suppose v is tangent to the level surface. Then what do we know? We know that phi would not change, because if you go tangent to the level surface, phi doesn't change, and therefore this difference must vanish to first order in v. So if that difference must vanish, it must mean that v dot grad phi is 0. What are we saying? If v is tangent to the level surface, then grad phi dot v is 0. Let me paraphrase this. It is simply saying that the gradient is perpendicular to the level surface of phi, because the gradient dotted with the level surface tangent vector is 0.
Sir, can you repeat the argument?
Yeah, sure. Yeah, I know that this is a bit hard the first time. What have we done? We have computed phi of r plus v minus phi of r. Okay, and I hope you will agree with me that we have got the answer as v dot the gradient of phi.
Yes.
Yeah, okay, great. So you're with me up to this stage. Of course, this is an approximation, but I'm going to, yeah, so I'm going to work at this approximation. Now, what are we saying? If v points tangent to the level surface of phi, okay, suppose that is the case as illustrated in this example and picture. Suppose v is tangent to the level surface of phi, then phi must not change. If we move a little bit along v. Do you agree with me? That is the definition of a level surface. If you move on a level surface, function doesn't change. Are you okay with this sentence, please?
Yes.
Very good, very good. So we are saying that i.e. left-hand side equal to 0 if v is tangent to level surface. Yeah, that is the change. The change is 0 if V is tangent to the level surface. So that must imply that the right-hand side is also 0. So this implies right-hand side is 0. Of course, if V points tangent to level surface, I will not repeat that hypothesis. So if so, we are saying RHS 0. But what does RHS 0 mean? It is saying the dot product of two vectors is 0. When does the dot product vanish? When two vectors are orthogonal. So this implies that grad phi is perpendicular to such V. Are you okay with this third sentence? Please tell me. Have I lost you? Yeah, please.
Sir,
yeah.
you were saying that
Yeah.
phi of r plus v is equal to phi of r on a level surface. So that is
true.
0.
Correct.
And if I take a small v connecting 2 points on a level surface, that means because it is 0, then v dot nabla phi should also be 0.
Exactly. Yeah. V dot nabla phi must also be 0. And now we are interpreting that quantity being 0. We are interpreting what it means for the gradient for this to vanish. It means that the gradient is orthogonal to V. Do you agree with that statement? I.e., grad phi is orthogonal to all tangent vectors to the level surface. Yeah, this is our conclusion. You take any tangent vector to the level surface, you will discover that nabla phi is orthogonal to it. So let me draw a picture. This is my level surface. There are many tangent vectors, this one, this direction, that direction, etc. Yeah, all the tangent vectors, all the hair on my head at this point are all tangent vectors to my skull. In all of those directions, nabla phi vanishes. I mean, let me not say that. In all those directions, nabla phi has no component. Nabla phi is orthogonal to all those vectors. So if a vector is orthogonal to all the vectors tangent to the top of my head, then nabla phi must point orthogonal to my head. Okay, that is all we are saying. Is that okay? Okay, maybe not so easy. Okay, anyway, as I said, you will need to think about this in your at your leisure and
Understood.
Oh, understood. Okay, great. So Oncon has given me some confidence. Okay, okay, thank you. So okay, unfortunately, we are already at 11:45. So anyway, this is a good place to stop. I encourage you to.
So 1 second. So does up till now I've understood that the nabla phi will be perpendicular to V. So this implies that it must point in the direction of most rapid increase.
No. That last conclusion we have not yet drawn. It must point either up or down from this level surface. Now, if you go up, it increases. If you go down, it decreases. So we have a last stage. We have to show that it actually increases. Yeah, that is the last stage of the argument that's written in this last sentence here. Yeah, so we have concluded so far that it must point either in the direction of most rapid increase or decrease of phi. That's all we have received so far. Now to show that final, yes, please.
Does that mean that if phi is a potential field,
yes,
then the level surfaces are equipotential surfaces?
Exactly, you have used a very appropriate term. So phi is a potential function, and the level surfaces of phi are the equipotential surfaces, and nabla phi or grad phi points perpendicular to the equipotentials. That's what we are saying. Who was that?
Krishanu.
Krishanu Bandyopadhyay, was it?
Yes, sir.
Okay, yeah. Does that address the terminology you introduced?
Yes, sir.
Okay, so the final stage in the argument is to actually compute phi. Yeah, so far we have simply said that it points perpendicular. Let us calculate phi after going a small distance along grad phi. Okay, let us suppose we start at R and go a small distance epsilon grad phi along the gradient. Epsilon is a positive small number. Now again we use a Taylor expansion. This by definition is equal to phi of R plus epsilon times grad phi dot grad phi. Do you get me? Yeah, say I'm taking phi of R plus epsilon grad phi. So by Taylor's approximation, it is the function at the original location plus the displacement vector, which is epsilon grad phi dotted with the gradient. That's what Taylor told us to do. Now you notice that this is the square of a vector, square of the length of a vector, grad phi dot grad phi. So that is greater than or equal to 0. And therefore, the function at the new location is more than the function at the old location, bounded below by the function at the old location, and therefore it's increasing. Thus, we have concluded that grad phi must point in the direction of most rapid increase of phi. Okay, so that is our conclusion. I'm sorry, I've gone slightly over time. Any question about this?
Sir, what did you do? V equal to epsilon nabla phi.
Exactly. I simply took V as epsilon nabla phi. See, previously we chose V tangent to the surface, right? So that was no good because the function doesn't change there. Now I choose V orthogonal to the surface, not just orthogonal, I choose it along the gradient. I choose V as epsilon grad phi and I ask, how does phi change? Does it increase? Does it decrease? This is the only question I'm asking. And what we find upon computing is that it increased. Do you follow?
Oh, so this means that the nabla phi will be along the most rapid increase of phi.
Exactly. We have reached that conclusion because
but it's little, I mean, little vague, right? I mean,
little vague. No, look, if you went along minus grad phi, see, suppose somebody said you go along minus grad phi, don't go along grad phi. Then we can ask, does phi increase or decrease? So then I will change the sign here. Yeah. And you will change the sign here also. And then you will find that the function decreases. So those were the only two options. We have already argued that you must go orthogonal to the level surface. That grad phi points orthogonal to the level surface. The question is, does it point in the direction of most rapid increase or decrease? That is the final question we are trying to answer. So we make a small step in the direction of grad phi and discover that the value of the function increases because you are adding to it a square. Is that all right? The logic?
no, I mean, now you were taking V equal to epsilon nabla phi, but that means that V and nabla phi are in same direction.
Yes.
So,
yes.
so, and you have shown that phi of this V, phi, not V, R plus V is greater than phi of R.
Exactly. Yeah.
So,
see, this V is not the same as the old V. That old V was tangent to the level surface. Now
yeah,
we are
I understand.
vector. Yeah.
But how does? But I can't understand still. How does it show that nabla phi will be in the increasing direction of phi? I cannot still understand. that.
Okay. That's the final point. See, what are we doing? We are computing phi. We are evaluating phi at a point. Which point is it? It is the original point translated by a little bit in the direction of nabla phi. Okay, so we are going along nabla phi. We are starting at a point. Nabla phi points this way. So when we say that grad phi points the direction of most rapid increase, what we mean is that if you start at a point and move a little bit along grad phi, the function will change and increase rapidly. That's what we're saying. So to test this, we have to actually compute it. Okay, so
I think now I get it. I think.
Okay, that's great. I'm very glad that you have tried to follow carefully and ask all your questions. I hope others have also benefited. But yeah, it's true. The argument we are given now is involves all the tools and techniques we have developed. So it's a bit of a mouthful. Please look at it once again in your leisure. Okay, so
So
we will,
there you took epsilon less than 1. Why?
yeah, because see, if I don't do that, then I must include also the quadratic term in the Taylor series. That is, if I make a big jump, then the leading
Oh,
Taylor
yeah,
approximation becomes inadequate.
Yeah, I get it. Okay.
Okay, good, good. Yeah.
Sir, may I say something?
Please repeat your question, Ota.
Sir, I am saying that I think we can mathematically prove like in somewhat, I think maybe easier way, that this direction vector differentiation, the thing I said to you earlier, that v cap dot nabla phi is that differentiation in that direction.
Okay, yeah.
Sir,
Sure.
can I tell what I am doing, if that is possible?
Okay, I mean, right now we are out of time, but okay, if you can briefly mention what you mean, you can do that.
Sir, I am thinking of taking a t as a parameter, as a real number. So I am taking phi of r plus v cap into t minus, and trying to find out what difference does that. And then I'm taking a partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. These three components are coming out as v cap, the x component of v cap into the x component of v cap into the x component of nabla phi, and the x component of this vector is coming out to be like this. Similarly, each component of that vector is that the corresponding component of v cap into the corresponding component of nabla phi by simple calculation.
Yeah.
So that, and now we have so in that way we can prove that v cap dot nabla phi is the direction differentiation, and in that way we can say that v cap, this direction differentiation will be the most when we point v cap in the direction of phi, in nabla phi only. Because
sure, yeah, you are right, yeah. And sure, I agree with what you're saying. I mean, what you're saying is essentially what we have done. So you have
yes, but what you have done is much more physics-like. It is much more important to physics than what I've just said.
Sure. Yeah, I'm fine either way. Yeah, you can, whatever you're comfortable with. Okay, any other comments from other students? Okay, if not, please go ahead, and we will meet on Tuesday once again next week. Yeah, if you have anything to discuss with me concerning practices, concerning sharing answers or taking somebody else's answer, please do approach me. I'm giving you a chance to tell your story if there is one. Okay, have a good afternoon then.